Yeah, you can hear me. Thanks to the organizers, Vijay, Jan, Johanna, Javier, and especially Dimitri for putting together this great workshop and for giving me the opportunity to speak. It's my first time in Brazil and I'm enjoying it very much. So I decided that today I'll talk about a recent piece of work I did, which I'll tell you about, something called the super virasoro minimal string. It's going to be mildly technical. I apologize for that. It's going to be old school string theory, and hopefully I've tried to keep the technicalities in the presentation to a minimum, but if there are details you'd like to know about, just come and ask me afterwards. So this is something I did with Zhenming Zheng, who at the time of writing was a undergraduate from Tsinghua, and he's joining Davis as a graduate student in the fall. Fingers crossed. And there's a very closely piece of related work by these folks, Beatrix Mollman, who is postdoc at IIS, Vladimir Narvolansky, who is also at the IIS, and Yanis Yares, who's in Paris. Okay, so I'll review. Basically, the essential content of the two papers is identical. We coordinated submission to the archive a couple of months ago. Okay, so I'll give you a broad motivation why I got interested in this problem, and then I'll review some previous work and then get to the punchline. So the broad question is the following. So we, of course, know of holographic dualities, and we've learned many things in the last 3 decades now. But preceding the holographic dualities, there were much simpler dual models between worldsheet strings and matrix models, primarily, which led to a lot of technical insight and physical picture of what string theory is about. In particular, they gave us a lot of insight into the perturbative and non-perturbative features of the worldsheet theory. So after all, I would have said that the onset of discovery of deep brains would have been probably not as clean had people not understood the duality between non-critical strings and matrix models in the early 90s. And again, as these theories themselves, these worldsheet theories themselves being dual to matrix models, they provide some kind of prototype for holographic dualities, one where there's no nice target space, but nevertheless, there is a nice dictionary between the worldsheet and matrix model data. One such is this minimal string, the C equals 1 string, or its supersymmetric version, and they traditionally have relied on non-critical string constructions, so basically coupling the Liouville CFT, which we'll talk about extensively, to free boson. So there's the picture roughly there's a target space where there is one free boson, which is time-like, it's target space time, and Liouville is like space direction. So it's two-dimensional string theory where space is cut off by some Liouville wall and you do scattering, and that scattering is related to matrix models duality. But you can ask, what are the primal ingredients of this kind of construction, and can you write down a worldsheet theory which has very primitive CFT data? And one such, which was discussed a couple of years ago by these folks, Collier, Eberhardt, Mollman, and Rodriguez, is the so-called virasoro minimal string, which I will review. And its building blocks are just simply Liouville theory. Okay. Liouville theory 1 with central charge C bigger than 25, and Liouville theory 1 with central charge C less than 1. The former is more familiar, and it's a conventional domain of definition of Liouville theory, as I'll review. The latter is less familiar, but nevertheless has been well understood for 2 decades now. A more interesting one, which I won't talk about, which these folks also discussed last year, is to couple 2 Liouville theories with central charges that are complex with some kind of CPT conjugation. And this again has a lot of interesting features, which I won't get into today, but we can talk about it in private afterwards. So why is this virasoro minimal string interesting? So for one, the motivation, and this was, I think, presaged in works by people like Thomas before, is that the worldsheet theory of this virasoro minimal string, not the target space theory, the worldsheet theory itself, it can be interpreted as a deformation of JT gravity. And in this context, the target space picture is complicated, and it's not something that I personally understand very well. But the worldsheet theory enjoys a nice web of dualities one with a matrix integral, and this matrix integral is a deformation of the JT gravity matrix integral, and that's why I claim that this can be best thought of as a deformation of the JT gravity. And this matrix integral is again something primal. It has a spectral density that's related to something universal in 2D CFT, namely the universal Cardy density of states. It's also related to interesting mathematics, namely to intersection theory on the moduli space of punctured Riemann surfaces, and through in the fact that the CFT data is related to chiral 3D gravity. It's also related to the Hilbert space of canonically quantized chiral gravity on Riemann surfaces through Liouville conformal blocks. And all of this was explained beautifully in this paper from 2 years ago. So what we're going to do is I'll review some of the ingredients that went into this, in particular the ingredients that connect up to the matrix integral. I won't talk about intersection theory or chiral gravity. But we're going to be interested in trying to do a supersymmetric generalization, which again has been thought about, but as you will see, there are interesting new technicalities that show up as we'll talk about the supersymmetric. Okay, so just as a warm-up, I'm just going to review, since people may not be totally familiar, what was done in this virasoro minimal string. So we'll just talk about the basic ingredients. So the essential ingredient is Liouville theory, and the modern perspective of Liouville theory is simply that it's a CFT for which I just give you some spectral data and OPE coefficients, and you bootstrap the rest. So the data is specified by the theory is specified by one parameter, B. I won't write down a classical Lagrangian. I'll write down one for supersymmetric theory later, but what I'm telling you is the quantum theory is not the classical theory. And the central charge is related, is given in terms of this B parameter. The spectrum is continuous above a gap, and the dimensions of primaries are some functions of B plus P squared. So P is taken to be on the half line running from 0 to infinity. Okay, so since P starts at 0, the minimum conformal dimension, let's say for the left movers, is Q squared over 8, and that puts a gap in the spectrum. So for in particular, this theory doesn't have the identity operator in its spectrum. And if I take B to be real, then the canonical domain is center charge bigger than 25. And so that specifies the set of conformal primaries. The only other piece of data I need to tell you is what is the 3-point function of these conformal primaries. I'll denote these primaries by VP, and the 3-point function of these VPs is known, and it was bootstrapped by the famous DOZZ formula 3 decades ago, and can be derived, as I'll show you in a while, by a nice trick of null state decoupling. Okay, so I just wrote down this formula. This formula is given in terms of some well-known explicit functions. They can be numerically evaluated. We don't need to know the details of these functions. Okay. So this one slide basically tells you what Liouville CFT is, and now you can go away and compute any observables you want in this Liouville CFT. I made some choices in writing down the structure constants, and the way I decided to write the structure constants is I normalize the 2-point function in a particular way, and the 2-point function is normalized such that the normalization is given by this formula of involving 2 cinches, but this formula arises as the modular crossing kernel of the vacuum character of virasoro written in terms of characters of primaries with weight P. Okay, so this is the famous Ponsonov-Teschner modular crossing kernel for virasoro characters, and this controls in 2D CFT the asymptotic density of states, and since that's why I referred previously to the statement that the virasoro CFT caps is governed by a spectral function that relates to Cardy density of states. Okay, and as I presaged, this data, namely the spectrum plus these OPE coefficients, completely specify the theory, because I can now obtain correlation functions on any closed Riemann surface by just conformal block decomposition. So I do an OPE expansion, integrate over conformal blocks, and now the only difference is that in contrast to usual formulas, I have a measure for the integration because of my normalization of 2-point functions. Good, so that's the background for Liouville theory. I'm happy to take questions before we go on to something more. Yeah.
Right?
This is not a string yet. This is just 2D
So you
CFT.
have to put gravity somehow.
I'm going to put gravity, yes. So far, this is just 2D CFT, and I've not done any string theory. Indeed, correct. There was a question? Yeah.
Greater than 24, you say?
Central charge is bigger than 25.
Okay.
25. Okay. That's for real parameter, real values of B. So let's take B to be, since the formula is symmetric under B goes to 1 over B. So let's take B to lie in the interval 0, 1. So B goes to 0, as you will see later, is what I will call the semiclassical limit. But we'll sort of see how to get beyond C equals 25. So right now the theory is only defined on the ray between C 25 and infinity.
But if you put a large central charge, you are not surpassing the limit of you need the central charge for the string? Or?
Coming.
Okay.
1 second. Okay. So to answer Horacio's question, I'm going to introduce one more CFT. So there's something you can do, which I'm not going to talk about. Namely, you can take B to be and make the central charge complex. You can take B off the real line and make it complex. And that allows you to define Liouville theory for all complex, almost all values in the of complex central charges, except for the ray running from -infinity to 1. The theory defined on the ray -infinity to 1 is slightly more complicated, and I'm going to define that theory for you now. Okay, and that will answer Horacio's question, because I'm going to define a theory which has arbitrarily negative central charge. So let me define a new theory, which I claim also satisfies the CFT consistency conditions, namely the bootstrap conditions. And that theory is parameterized by a B. And for the rest of the talk, I'm going to emphasize that please pay attention to my fonts, because whenever I say something time-like, my fonts are sans serif, as opposed to when I say something space-like, where my fonts have serifs. Okay, so people like to put hats. I didn't like to put hats, so you get my fonts. So now the central charge is 1 minus 6q squared, and C is less than 1, and this q is 1 over b minus b. So you might have thought that the right way to do this is to just take b and replace it by I times sans serif b. Okay. It sort of works, but it's not quite. And again, the primaries of this theory are labeled by a real momentum, and the dimensions are given by these values. Okay? This is not a unitary theory, but it's fine as a CFT, and it certainly will be fine when I put it together to make a worldsheet string. The structure constants of this theory were initially discovered 2 decades ago by realizing that the DOCZ formula had a second solution, which gives a new set of conditions, which I will review later when I talk about the supersymmetric theory. And this gives you the structure constant of the time-like theory. So the structure constant of the time-like theory, again, the C here is sans serif. And these structure constants turn out to be related to the structure constants of the space-like theory by an inversion and complexification of momentum. Okay? So this was analytically derived by Zamolodchikov and Kostov and Peskova 2 decades ago, and I emphasize has been numerically checked to satisfy crossing in this very beautiful paper from about 10 years ago by Ribot and Santa Chiara, but also later by Min-Jae Cho, Bruno Balthazar, and Ji Yin in the context of this C equals 1 string theory. Okay. While it sounds like getting from the space-like Liouville theory to this time-like domain where C is less than 1 seems like an analytic continuation, I should warn you that it's not quite the same thing, because when I do the conformal block decomposition of higher point correlators, there's a contour of integration I need to pick for these time-like momenta, and that contour is not the conventional contour. So there's some technical details which I'm hiding under the rug in defining what this time-like theory is, but all I want you to take away from this slide is that the time-like theory by itself is well defined, and we can work with it as a CFT. Okay, so now I have 2 theories, one with central charge bigger than 25 and one with central charge less than 1. And so I can put them together and add them up to make total central charge 26 and couple this to the worldsheet gravity, which basically means adding to this two CFTs, the BC ghost system. If I do that, I chose my parameterization cleverly, that all it means is that these two B parameters get to be equal, so the sans serif and the serif B's are the same for the string construction. Okay. Moreover, the data that you get for the worldsheet primaries, namely the physical vertex operators that satisfy virasoro constraints on the worldsheet, are simply so these are the unintegrated vertex operators. They are the space-like Liouville vertex operator times the time-like Liouville vertex operator, with the momenta for the time-like guy being I times the space-like momentum. The physical state condition basically says time-like momentum is I times space-like momentum. And then the CC tilde is just to say that this is the primaries basically satisfy virasoro constraints if they're not integrated. If I'm going to integrate them, you can remove the CC tilde. Okay, so there's some very nice things about these guys. So because of the relation between the structure constants, the 3-point function on the worldsheet, which basically has no moduli integration, so I just fix 3 points on the worldsheet and compute the sphere diagram, and so that 3-point function is a constant, okay, because of this relation that these two things are inverses of each other. Second, yes, Misha. These are the only vertex operators because the Liouville theory has the only primaries in Liouville theory are VP. Are VP? You're probably worried about discrete states.
Well, no, I'm worried about some other combinations of P that will
satisfy virasoro constraints. Right. There aren't any.
Okay.
Yeah. So, I mean, there's something else you can worry about, which is discrete states that exist in Liouville theory at special values of momenta, so they probably show up. But the external vertex operators, as you well know in Liouville theory, are just the scattering states.
I mean, the two matrix model has more observables in principle. I mean, you can build all kinds of usually the observables here are made out of a single matrix out of the two, right?
Correct.
So,
but there's only one matrix. There's only one spectral density. Which I'll tell you what the matrix model is in a second.
Yeah, but there are two matrices. So in principle, there are two spectral densities that are correlated.
There's only one matrix, I think. There's only one.
Isn't this like
density.
the two matrix model? I'm sorry, maybe I'm confusing.
Yeah, I think there's just one spectral density. I'll tell you what it is in a second. There's one nice feature also with this inversion relation. Of course, this statement that the 3-point functions are related by inverses is nice, and it's simple at the level of 3-point functions. But if I do higher point functions, I actually have to compute correlators of some number of VPs and some number of V sans serif P's. And that involves integration over momenta. And in those, the structure constants don't necessarily cancel. Nevertheless, if you do worldsheet calculations, unlike conventional worldsheet string theory, the integrals that you need, the integrands that you need to integrate over the worldsheet moduli space are well behaved, and the integrals are convergent. So this theory basically can be put on a computer and studied, which is roughly speaking what these folks did for some of these observables. Okay, so the amplitudes of this theory, the physical string amplitudes, are basically correlate endpoint functions of the space-like theory, endpoint functions of the time-like theory, dressed with some ghost correlators of the BC system, integrated over the n-punctured genus G Riemann surface moduli space. So if I'm computing the genus G amplitude, I'll take a genus G surface with n punctures and do this moduli space integral. What do these amplitudes compute? The claim is that these amplitude compute volumes, at quote-unquote quantum volumes, of the moduli space of marked Riemann surfaces with geodesic boundaries, very much the same as the JT gravity matrix model computes volumes of moduli spaces of Riemann surfaces with geodesic boundaries, except that when I say quantum volumes, I just mean that these volumes are not the canonical volumes with respect to the Weil-Petersen measure, but rather deformed by this B parameter. So the matrix model in question, the double scale matrix model, is defined by the spectral density I flashed before, which is given by this two factors of sinh, which you will notice if I take B to 0, the semi-classical limit will reduce to the JT gravity spectral density. Okay. The data of the Liouville theory, which is completely specified by these momenta, maps to the lengths of these geodesic boundaries. Okay, so this integral is some function of these PIs, and those PIs map to the boundaries. So you can think of this as closed Riemann surface with some number of geodesic boundaries. Okay. These folks also discussed how to talk about boundary conditions, trumpets, and double trumpets, which I will not talk about because I'm not going to talk about open string boundary conditions for these theories, Debrand boundary conditions for these theories. Okay, and again, I just re-emphasize that this is basically the JT gravity matrix model arises in the semi-classical limit of this guy. Okay, so hopefully you got a sense of what the theory is and what it can do for you. So now I'll try to switch gears and talk about the super Liouville theory, unless there are questions about the timeline. Yeah. You're asking whether the matrix interpretation of the
S-matrix.
S-matrix element. Not quite, for the following reason. So the usual. So let me do something that for anchoring your intuition. So if you sort of replace a time like Liouville theory with a time like boson, then you have a time direction, which gives you a notion of in and out states, and you can prepare states in the weak coupling region of Liouville, which is far from the Liouville wall, which are the scattering states, and you can scatter them off the Liouville wall. And in the usual C equals 1 case, these are the things that map to the matrix model observables. Right? And either they are in the bosonic theory, they're one-sided matrix model. In the supersymmetric theory, they're a two-sided, fully filled matrix model. In this case, you have a Liouville wall in space, but time also is a Liouville theory. So you have a Liouville wall somewhere in your past or future, depending on how you've decided to orient the time-like theory. So I would say that there is a sort of asymptotic region. Let's say we've oriented the time-like Liouville wall to the past in the far future, where you can talk about free states, but it's not clear where these free states are coming from. Victor has a nice paper from actually before they wrote this Liouville-Virasoro minimal string paper, trying to interpret this theory as some kind of string world sheet cosmology, where you sort of have some kind of Big Bang, which is a strong coupling region of the time-like theory, which then evolves into free particles into the future, or vice versa. Okay. But that's the sort of extent to which there is a target space picture, and I think it would be worthwhile asking what this means. Yes, Roberto.
Of the model.
Yeah.
So you say that well, you have a limit where this reduces to JT gravity. JT gravity, of course, we know that it also arises from higher dimensional
yes.
Black holes.
Yes.
If you perturb this a little bit away from JT gravity, because I imagine that for finite J away from this, then yes. The space-time interpretation is complicated. Do you have any?
Great question. I don't know. So you could ask, if I talk about this particular matrix model,
yes.
What do these B-deformed theories compute? I don't have a good idea.
Yeah, but deforming a little bit away from JT, maybe it can give you some interpretation of.
Yes, it's a great question. Yeah. Yes. It's not a Q deformation, as far as I know. Yes. All right. So shall we proceed? Make our life slightly more complicated. All right. So the super Liouville theory I want to talk about is a theory with 1,1 supersymmetry on the world sheet, and you can think of it as being described by a classical action. This time I did write a classical action just to orient you, where there's a superfield phi, whose bottom component is the classical Liouville field. It has two fermions, a right mover and a left mover, and an auxiliary that you can integrate out. There's a superpotential, which is e to the b superfield phi. If you write out the coupling is psi tilde e to the b phi. Okay, so remember this, because one thing that's important about this theory is that there's only one left mover and one right moving fermion. So there's slightly more complicated discussion of what the spectrum of the theory is compared to usual worldsheet constructions. Okay, the quantum theory again can be, the classical theory is of course the Lagrangian is what it is, but the quantum theory is not contingent on what this Lagrangian is. And the quantum theory defines a superconformal field theory with C bigger than 27 halves. And again, I'll parameterize the central charge by this parameter B. Okay. The main difference at first sight is that we have fermions on the worldsheet, so we have to discuss what boundary conditions we're going to put on the fermions. So we have to decide what to do about the spatial boundary conditions, and therefore we have Levy-Schwartz and Ramond sectors. And the issue here is that usually when you do textbook string theory, you sort of have pairs of fermions which you decide to bosonize into spin fields, and then you sort of talk about the vertex operators in terms of bosonic degrees of freedom. Here you have a single right moving and a single left moving fermions. So you have to define the Ramond vertex operators like in the Ising model in terms of spin and disorder operators. But those details aside, I can just tell you what the spectrum is, and then we can sort of define the theory in terms of the spectral data and the OPE coefficients. So in the Levy-Schwartz sector, there is a superconformal primary, which I will call VP in analogy with the bosonic theory. It has three descendants, global descendants, which are descendants obtained by acting with the supercurrent minus half on the left and supercurrent minus half on the right. Okay, so I've written it as a superfield, but lambda p is g minus half VP, and lambda tilde p is g tilde minus half VP. Okay, there's a left moving and right moving conserved spin 3/2 current because it's superconformal theory. These guys are fermionic because they carry spin. They're obtained by acting with a spin half generator. There is a second spinless field, which is the double descendant g minus half g tilde minus half. Okay, so the dimension of V is again like in the bosonic theory, it's simply given by some shift of the q squared over 8 by p squared. And I'll normalize the VV correlator by, again, the same kind of normalization I did before, except that now the factors are slightly different because I care about superconformal characters. So this factor is basically the modular crossing kernel between the trace in the NS sector of the with no minus 1 to the f. The Ramond sector, like in the Ising model, has two degenerate primaries, and I'll just classify them based on what their parity is under worldsheet fermion number. So I'll call them R plus and minus. One of them has positive parity under worldsheet fermion number, the other has negative parity. And the normalization of the Ramond vertex operators is in terms of a different factor, which is given in terms of the modular crossing kernel with trace of NS with minus 1 to the f. So it's a cosh. Okay. So that's the data. There are many more vertex operators because we've enlarged our date of the theory. But you might say, but they still have superconformal invariance, so maybe life is not too bad. Turns out life is slightly more complicated, because even after using superconformal word identities, turns out there are 4 independent structure constants that I need to specify the theory. So unlike the bosonic case where there was one class of vertex operators and one set of OPE coefficients, now I have 4 functions I need to give you. Okay, all of these functions can be written down in terms of the same kind of functions I showed you before, so I'm not going to show you those functions, but I will tell you that the non-trivial 4-point functions I care about are 2 in the NS sector and 2 involving NS and Ramond vertex operators. Every other correlator that's non-vanishing can be obtained from these by superconformal word identities, and the the data I'll call is when I have 3 V's, I'll call that structure constant CV, and there's a non-trivial NS 3-point function involving 2 V's and 1 W, which I'll call CW. And then there are 2 structure constants involving V, and then the Ramon vertex operators, which for reasons I've defined in different parity combinations. Okay, there's an even and odd, but that's what the answers look like. Okay, so these structure constants are known, and again, they've been known for 3 decades. They were worked out very soon after the DOZZ formula by these folks, and they're well discussed in the literature. Good. Okay, so that's the data of the Liouville theory with central charge bigger than 27 halves. We want to make a superstring, so we want to make the worldsheet central charge 15. So I have to define another Liouville theory with central charge less than 3 halves. So I'll do that, but before I do that, I'll tell you how these structure constants are obtained, which also sort of explains where the DOZZ formula comes from. Okay. So the logic, which goes back to trig by Teschner, is the following. The generic module of a CFT, parameterized by this B in Liouville theory, has null states at special values of momentum. You can write down a 4-point function involving 3 physical vertex operators and 1 degenerate vertex operator. So the details of what is vertex operator are not important. What is important is that the fusion of this degenerate operator with any of the primaries produces a finite number of terms on the right hand side. Given this, you can, and I've written down what the fusion rules are with some particular coefficients which involve gamma functions. And if you massage the degenerate OPE and rewrite the correlator of the 4-point correlator in terms of 3-point correlators, in the null state decoupling statement can be translated into a functional relation for the structure constants. Okay, so there's a functional relation between, in this case for the supersymmetric theory, between CW and CV, where one of the momenta is shifted by parity combinations of IB/2. Okay, and that ratio is given by some ratio of gamma functions. Likewise, there's a similar relation with B replaced by 1/B. So there are 2 sets of functional relations in this theory, which tell you something about ratios of structure constants, and then you can just go ahead and ask yourself, are there solutions to these functional relations that fix the structure constants? Okay, and since everything is in terms of gamma functions, you can sort of guess that when the dust settles, you just need appropriate functions which have some recursion under shifts by B and 1/B. Okay, and these are the special functions, these Barnes double gamma functions, which show up in the DOZZ formula. Okay, so this is what is usually called the functional shift relations in super Liouville theory for the NS sector. There's a similar relation in the Ramon sector, and by solving these, we just obtain the structure constants. Okay, so explicit formulas, which I'm not writing, for these 4 structure constants were obtained by these folks by precisely doing this. However, what they didn't do, and what wasn't done till recently, is there's a second solution to the structure constant functional relations, and that defines the time lag theory. Okay, so for now I'll just tell you the answers, and by defining what the time lag theory is. So again, the time lag theory I'm going to define by my sans serif parameter, and the central charge this time is bounded from above by 3 halves. Okay, and the spectrum is isomorphic. There's a superconformal primary in the NS sector, and its double descendant W, which is also spinless, and there are 2 degenerate vertex operators in the Ramon sector. And again, there have to be 4 structure constants, because that structure constant data was completely fixed by superconformal word identities. It was theory agnostic. So by solving the shift relations, we determined, as did these folks, the structure constants for the space lag theory. And here's the answer. I highlight 2 features of this. and this will also come back to a question that Horacio asked, which I will claim later, that even though Liouville theory doesn't need string theory, Liouville theory knows about string theory. That the structure constant involving 3 V's in the time-like theory gets related to the structure constants involving 2 V's and 1 W in the space-like theory by inversion, and vice versa. And again, the even and odd parity guys get swapped in this relation. It's the same kind of inversion, but some factors get flipped around. Okay? And I will leave you to muse for the next 15 minutes why that happened, because I claim it had to happen. I put in, for clarity, 2 parameters, eta W and eta R, because the shift relations, and what I'm going to show you in a second, that the fact that these actually satisfy bootstrap constraints, are agnostic to overall signs. Okay? A priori, even in the bosonic theory, I could define the time-like theory with some signs in the structure constant, nothing would have happened. It's not a unitary theory, there's no fixed sign for a 3-point function. So, for reasons which I'll explain later, there were 2 signs that we put in our paper. I think I know how to explain part of them, but you will see there's a subtlety in how to interpret this. Okay? But message so far I want you to take is the super Liouville theories are just as well defined as the bosonic theory, and we have all the data for them, both in the regime where the central charge exceeds 27 halves and in the regime where the central charge is less than 3 halves. Okay? And just to convince you that we actually did some work, this is the numerical check of crossing for 4-point functions, where I've plotted it's really hard to see because there are 2 data points at every point here, which are overlapping data for 2 different channels of the 4-point function, where I've swapped the intermediate operators 3, 2 and 2, 3. Yeah, for different values of momentum. So, and again, I emphasize that eta W and eta R are signs, plus minus 1, and this check is insensitive to those signs. Very good? Okay, so now we can talk about strings, unless there are questions about what super Liouville theory is. Good. All right, so now we are in business. So let's do the following. Let's just say we take a space-like and a time-like super Liouville theory, and then couple it to n equals 1, 1 worldsheet supergravity. Okay? So let's just convince ourselves what we expect, and this was already presaged in a nice paper by Thomas from 5 years ago. Let's just ask what happens in the classical limit. Okay? So we look at the worldsheet theory in superconformal gauge, where I have a space-like Liouville theory whose Lagrangian I flashed, and now here's a time-like theory where I've defined the time-like super Liouville field as capital psi. Okay, and it's time-like because the kinetic energy is negative for this time-like theory. You can do a field redefinition of this combination of this phi and psi, and rewrite this Lagrangian in a form that you probably saw in Thomas's talk last week, which basically gives you something like JT with a Sinch potential. And by some integration by parts, you can rewrite this as super JT theory on the worldsheet. Okay, so again, our anchor point was that there is some classical theory, which is basically super JT, and now we want to sort of talk about what a quantum theory is and ask what the observables are. Okay, so again, we are putting together the space-like and time-like super Liouville theories, and we now have to gauge super diffuse on times while on the worldsheet. So we have both the BC and the beta gamma goes, and requiring that the total central charge of all this mess be 0 tells me that again the Liouville parameters are related by the space-like and time-like values being equal. Okay. So far nothing changed, but now life gets complicated, because I have to impose mutual locality between various vertex operators. Namely, I need to impose GSO projection on the worldsheet. Okay. Now this is a theory with 1, 1 supersymmetry, and as I promised, there is no pairing of fermions because there is no separate left and right moving fermion pairs that I can sort of combine in this theory. It's only true, as I was answering in earlier, in the asymptotic far future, let's say, if I've oriented my time like that in a particular way. So there is no type 2 chiral GSO projection for these theories. All there is a diagonal GSO, which gives me the analog of type 0 theories, okay? Which is the same as in the case of the minimal string, because you just take a Liouville and couple it to free boson, you don't get type 2 theories. Okay, so there's a fermion number there's a total fermion number for the space-like Liouville theory, the total fermion number for the time-like Liouville theory, and I'll call their product the matter fermion number, and the worldsheet fermion number will involve that matter fermion number and the fermion number for this BC beta gamma ghost system. Okay. I have to make one more choice. Okay, so this is not in the paper, so let me explain this. This came about after we put out our paper in discussions with Beatrix and Lorenz. I have to decide what supercurrent I want to couple to gravity. So one choice is to say I take the space-like and time-like supercurrents and add them up, both on the left and right, and couple that to gauge that current. Don't worry about these phases and signs, they're just cocycle factors to make sure that these actually satisfy the right commutation relations. But I could also define a different combination where I add up the left moving currents, but I subtract the right moving currents. Okay, so this is a discrete Z2 choice. And in addition, I get to make a choice on how I'm GSO projecting. I can project onto states with -1 to the F worldsheet equals +1, or to project onto -1 to the F worldsheet equals -1. So all told, there appear to be 4 choices, 2 Z2s that I get to make, which lead to 4 inequivalent string constructs. In our paper, we only talk about 2 because we made our canonical choice of saying that the supercurrent is just the first line. Okay? I'll give these names. These names are just conventions at this point. For diagonal GSO projection, the textbook terminology would be that the GSO projection with -1 to the F equals +1 is 0b, and -1 to the F equals -1 is 0a. So I'll call them the same thing, but then I'll call 0a prime and 0b prime the opposite thing with these primed supercharges. Okay? Okay. And now we can ask, what are the vertex operators and what are their observables from the worldsheet point of view? Again, there's a complication because this is a superstring, so I have to tell you first, I'll tell you what the story is in the NS sector, and I have to tell you what the vertex operators are in different representatives because of the presence of supermoduli. So this is the usual story of picture changing operators in worldsheet. So I'll give you the answer in the canonical picture for NS vertex operators, which is -1 picture. There's a unique vertex operator, like in the bosonic theory, which is just the product of the 2 V's. Because these are superconformal primaries, they satisfy super virasoro conditions. Okay, and they're dressed with the BC ghosts and the beta gamma ghosts, which are bosonized into this var phi. But when I'm computing observables, I need to soak up fermionic moduli on the worldsheet, which is usually canonically done by changing picture. And if I switch to the 0,0 picture, which involves acting on these vertex operators with g minus half, g tilde minus half of the total matter theory, I get 2 different representatives depending on my choice of g and g prime. The relative sign here manifests as this relative sign between the v's and w's. Okay? So the 4 theories all have the same NS vertex operator in the -1 picture, but 2 of them, the unprimed theories, have a different representative from the other 2 with the primed theories in the 0,0 picture. Okay? And this will be important in a second. In the Ramond sector, the vertex operators again depend on our choices. I'll just say that two of the theories, what I call conventionally 0a and 0b prime, they do not have Ramond vertex operators. This is familiar to those of you who've known about the C equals 1 type 0 string, 0a string, which does not have Ramond states, it has only Ramond fluxes. And in the other two theories, there are Ramond vertex operators, but there are different chiral combinations of the space-like and time-like guys. Okay, so one is plus minus, the other is plus plus, depending on how I'm doing the projection. Yeah. A lot of this is similar to what was analyzed in the case of minimal superstring by Maldacena, Klebanov, and Seiberg, and by Seiberg and Chi. But in most of the discussion, as far as I know, only two of these theories were studied. I don't see why the other two theories were not examined. Okay, so now let's do the simplest calculation, which is namely compute the 3-point function of these vertex operators. Okay. So in the NS sector, I had simple vertex operators, and you say, let's just put 3 NS vertex operators together. To do a calculation in the superstring, you have to remember the following. While on the sphere, when you fix, there's a conformal killing group, you fix 3 vertex operators to soak up the conformal killing vectors. You fix their positions at 0, 1, and infinity. However, the supersphere, CP1/1, has a fermionic modulus, which means the beta gamma system has a modulus that you have to integrate over. The trick that's usually played is to shift the picture of one of the vertex operators to 0, 0 picture and avoid doing the integral over the fermionic modulus. Okay? The right statement is that if I have a sphere with NS vertex operators, or a genus G surface with n vertex operators, the moduli space dimension is a super manifold with these many bosonic directions and these many fermionic directions. So for G equals 0 and NS equals 3, I have no bosonic moduli, but I have one fermionic modulus. But there's a way out around it, which is namely switch the picture, and one of these vertex operators is in a 0, 0 picture. Okay? But now you realize that time-like Liouville theory was very, very smart. Because had I been computing correlators of 3 V's, and I wanted a pure number, it had better be that the time-like correlator of 3 V's got related to the time-like correlator of space-like correlator of 3 V's. But because of picture changing, what the third vertex operator involves a VW combination. Okay? So you get a pure number, but you get a pure number because of picture changing. Okay, the inversion relations between space-like and time-like Liouville theories appear to be aware that you want to apply this to string theory. No reason for them, but it's a nice consistency check. Anyway, when the dust settles, you get pure numbers, and I've written those pure numbers for various of these correlators in terms of the signs I introduced. Okay? So if eta w is +1, this guy is 0 and this guy is 2, and eta r is +1, this guy is 0 and this guy is 2, up to factors that I've ignored. Okay, so this is the calculation from the worldsheet, being agnostic about any expectation from matrix models. Okay, now let's ask what happens from the matrix model. So the super JT matrix model was studied by Stanford and Witten, and we can sort of take inspiration from that and from some other work that was done by Cliff Johnson, who actually looked at the matrix model with the spectral curves I showed. Claim, I'll just tell you their claims. They studied the matrix model and they said the 0B theory has no fermion number symmetry, and as a result, what you should be computing is volumes of moduli spaces of super Riemann surfaces with some number of geodesic boundaries. The geodesic boundaries can have NS boundary conditions or Raman boundary conditions. Okay. However, they argued that all of those volumes are identically zero to all orders in perturbation theory. Okay, the argument is actually very simple. Let me quickly motivate the argument. So, a G equals 0 and 3 boundaries, which is, I have a moduli space which is a supermanifold whose dimension is 0/1, and volumes of a supermanifold with more fermionic directions than bosonic directions are just 0 because of the integral of the fermionic directions. They also showed that given the matrix model discussion, there is a topological recursion with this data as a seed for topological recursion, and therefore it follows, at least in the NS sector, that every amplitude with NS boundaries is just plain 0. Okay? So, of course, I can make things 0 by a choice of sign for eta w. So, let's say I chose eta w to be +1, and it's this theory that has that sign. Okay? There's another argument for why the amplitudes are 0. This is a matrix model argument. The spectral curve for this matrix model is expected to be this cosh, which is edge free, and that spectral curve being edge free has no perturbative observables. There, thank you. I'm close to being done. Yes. Maybe we should.
I am.
You should.
Worried,
let's see. Let me think. Did I get this right first? I think you get some normalization that just gives you a single cosh. Let me double check.
Okay.
So I think there is no divergence in the limit. Do you know, Thomas? Yes. So that's a repulsion from the. Yes. Yeah. So I think it's okay. It's just a statement that there are no BPS states in this problem, unlike the n equals 2 case.
Okay, maybe you can explain that later to me.
The theory that actually has non-trivial observables is a 0A theory, which does have a fermion number operator, and so you can weight moduli space volumes by -1 to the f, and so that's usually what's called this mod 2 index, and it doesn't give you any non-zero observables at genus on the sphere, but it does give you higher genus observables which are non-vanishing. I emphasize something remarkable about this, namely that there is a perturbative string construction which has no perturbative observables. I mean, this is the ideal playground for understanding non-perturbative string theory. Okay, we are far from it for reasons I will now explain, but I think it's a remarkable construction which is not topological, but has no interesting observables in perturbation theory. Okay, so I'll just summarize some of the statements. So the matrix model intuition tells us that we should have the 3-point amplitude with NS punctures be vanishing in both the 0A and 0B theories. And I introduce these signs mostly to orient you in the eta W and eta R, but you can trade those signs for my choice of supercurrent combinations. Okay, because you see, let me explain this in the following. This choice of signs in what supercurrent I actually use to couple to the supergravity tells me what the relative sign is between V's and W's in the picture 0 operator. But it's the same kind of choice of sign I would care about if I sort of choose to redefine my time-like structure constants by putting CW to be minus the CV. Okay, so there's no so it's not like the 8 choices, there are only 4 choices, and we can just set eta w and eta r to 1 once and for all, and ask what happens. Okay? So the thing that's confusing me, and this is something we're trying to figure out, is the ideal choice is to basically just fix the CFT data once and for all by saying that the signs in the structure constants are just unity, these signs are just spurious, and then we would end up with this slightly funny situation where some of these, the NS amplitudes can vanish for these unprimed theories, but the Ramond amplitudes vanish for the unprimed theories. And that seems a bit odd, so there's something missing in my understanding of what's going on. So, as I said, I think one should just fix the structure constant and use the string theory, define the string theory with that data. Okay? So we're still trying to figure out what's happening with the super JT theory and what the observables are. So I'll sort of end by saying some general comments by pointing out that this is a simple theory that you can construct with some very basic data, namely some supersymmetric analog of Liouville theory. But as you saw, there's lots of intricate moving parts in this theory that somehow have to conspire to make things work, and make things work with respect to expectations from the matrix model. And there are also lots of choices that are unconventional from the point of view of usually how we construct geoprojected physical states. We are currently thinking about how to refine this dictionary and say various statements about it. So there's sort of a brute force approach, which turns out can be done, but it's annoyingly complicated. Namely, to just compute higher point amplitudes on the worldsheet, which again, we have all the data, so we can just compute 4-point functions in the Liouville theories and integrate them on the moduli, and check whether they conform to our expectations. Okay, so that's in progress. So I think we think the 4-point function of the sphere and the 1-point function of the torus are within reach. But I think that would not be satisfactory in establishing the duality. I think what would be really satisfactory is to see the kind of thing that was seen in the matrix model, namely to derive the matrix model topological recursion directly from the worldsheet. And here I emphasize that this has not even been done for the bosonic model. But the target, I think, in the super symmetric case is slightly easier, because you're shooting for some, not some functions of these boundary geodesic lengths, but zeros. It's be easy to see whether something is 0 or not. Okay? There's a analogous question related to sort of what I did not talk about, namely to define what super virasoro QFT is, which is the data of chiral 3D gravity. Okay? And the same statement as before, namely to prove vanishing theorems for string amplitudes without actual direct computation. All right, I think that's all I wanted to say. So let me thank you and take questions.
Okay, questions?
So, for standard string theory, so there exists the n equal to string, which has a critical dimension 4, which yes, rules out for Kaluza-Klein compactification, but it seems very fit with your minimal string ideology. So my question is the following. Is there any extension of this result to n equal to super virasoro with n equal to super Liouville?
Okay. Yes, it's a great question. People have been thinking about it. So just to orient people, the theory I talked about is gauging n equals 1, 1 worldsheet supergravity. The famous theory that is not very well known, which is to gauge n equals 2, 2 supergravity on the worldsheet and couple it to 2, 2 superconformal field theories. And indeed, the critical dimension is 4, but it's a critical dimension is 4 with Kähler target. N equals 2 Liouville theory is known, and it's supposed to be dual to some coset sigma model, namely a Sigard coset SL2 mod U1, with n equals to supersymmetry. As far as I know, its structure constants have not been bootstrapped, apart from noting the duality to this case. Your question is actually interesting for physical reasons. As Thomas presaged, in theories it's n equals 1 supersymmetry. Such, and as Roberto said, such theories don't appear in the near horizon limit of supersymmetric black holes. The super JT theories don't appear. But n equals 2 super JT does appear, and it controls the degeneracy of BPS states in these black holes. So having a worldsheet construction with n equals 2 Liouville would give you a worldsheet understanding of some of these BPS degeneracy counting. So in that context, this question is very interesting, but I think a lot more groundwork needs to be done. Namely, even the space-like n equals 2 Liouville theory needs to be better understood, let alone the time-like case, before we get there.
In that case, which could be the counting of the central charge? Because you said that it's 15 for the super
yes,
super Liouville would be something.
Yeah. So let me see. So it's 4. Total target space dimension is 4, which means it's 4 bosonic, and then there are I guess it's 10, right? Because it's 3 fermions on the left and 3 fermions on the right. So,
thank you.
Yeah, so not much is known about this, but this is something that various people have wanted to do, but as far as I know, nobody has done.
Thanks.
It is also slightly simpler for reasons which I can explain, namely that 2,2 supersymmetry has spectral flow, so there are no separate NS and R sectors, you just integrate over them.
Maybe we have time for one more question.
So what you said that this theory does not compute, does not work for finite geodesic length boundary somehow. What was that comment precisely?
No. So what it does compute is, so what I think it should compute, let's say for NS punctures, it should compute volumes of moduli spaces of super Riemann surfaces with NS boundary conditions, with moment, with boundary length P.
So is there a version of like the disk computation here?
There is a version of the disk computation. We have some preliminary results which seem to agree with things that people have computed, like what Thomas has computed, but we're not satisfied with the derivation, so we didn't write this up. It's a question of thinking about deep-range states in the time-like theory, which we did some naive thing and it seems to work, but it needs to be sort of sharpened. But exactly, so the disk answer seems to work, but there are some subtleties in. And the trumpet also seems to work, again, with some modular, some subtleties.
I see. Thanks.
So just a side question, this shift relations, do they have analogs in like a compact case?
Sorry, what do you mean by the compact case?
Like Wezumino with...
yes, so, there are some peculiar properties for the shift relations. If you take the values of B that bring you, okay, so maybe I say it this way. So think in this complex plane, in the complex C plane, and I define the theory here initially, and then I define the theory here. But you can take the shift relations here and take an excursion into the complex plane and try to come down to the virasoro minimal models from above by taking C to specific values. And they usually give you the right answers for the virasoro minimal models. But just to emphasize, it's not the same thing as coming along the time-like direction. Just as it's not the case that C equals 1, time-like Liouville is the free boson.
Okay, let's thank Rangamani again. Okay, so now coffee break. We resume at 10:30, but I will ask you to remain here so that we take a picture before we go.